Let's continue with chapter 5 in total resistance. Parallel circuits finding total resistance. So we saw from the previous video that in order to find the total resistance of a fully parallel resistor circuit, we will have to do the reciprocal of the summation of the reciprocals. But in this case, if we have two resistors, if the circuit that we are analyzing only has two branches, which means only two resistors connected in parallel, then we can use this special formula, which states that the R total or the R equivalent of these resistors would be the multiplication of the two resistors divided by the addition of the two resistors. That's, again, it can only be used if there are only two resistors in the circuit. If we have three or more resistors in the circuit, we will have to use the standard formula, or we can start doing two resistors at a time. If we don't want to use this formula, we can start let's say there was three resistors, we will do two first, and then the equivalent of that, we will do the same formula again with the other resistors that we didn't use. In the sections for problems and examples, I'll do an example like that so you'll see what I mean by that. So the question here is that what is the total resistance if we have in R1 equals to 27 kilo ohms and in R2 of 56 kilo ohms. To start with, we know that the equivalent of the resultant resistance should be less than 27 because it is a parallel circuit. So if I multiply these two and I divide it by the summation of the two, I get 18.2 kilo ohms resistor. Okay, so now let's go ahead and start analyzing a parallel circuit. So we have our source, we have our three different branches, and now we are going to calculate the voltage, the power, and the currents. So like I said before, a characteristic of a fully parallel circuit is that the voltage across each individual resistor, it is the voltage source. So in the previous example, they assumed that the voltage source was 5 volts. So B1 is 5, B2 is 5, B3 is 5, and B source is 5. The different values of the resistors are given. So now using Ohm's law, we can find the current. So we said that the current is majority of the current is going to travel through the branch that has the least amount of resistance. So in that case will be R1. So we expect that the R1 or the I1 is the highest of all the currents. So then we use Ohm's law and we get, Ohm's law says that how do we find current? Current is voltage divided by resistance. That's why we know that the current is going to go through here, the majority of it. So 5 divided by 680, we get 7.4 milliamps. Then I2 should be higher than 2.2 because R2 is less than R2, so we get 3.3. I3, we get 2.3 milliamps. To find the I source, the current supplied by the voltage source, we would find the R total and divide the voltage source by the R total, or we can add I1, I2, and I3 because we know that in here I source comes and then it's going to split one way, it's going to split another way, and it's going to split another way. So if we add them up, we are going to get the I total, and in this case was 13 milliamps. To find the power, it is not affected whether it is a series circuit or it is a a parallel circuit. Power always going to add up to a power source. Whatever the power is produced by the source, whatever power is produced by the source, it has to be consumed by each individual resistor, okay? So with that, we are going to introduce a version of the KVL that we have for the series circuit. So here is going to be a Kirchhoff's current law, better known as KCL, Kirchhoff's current law, KCL. For voltage, we had Kirchhoff voltage law, or KVL, series circuit. KCL it is for parallel circuits because it has to do with the current, which is what is going to be splitting. So a voltage stays the same, current gets split. So as a series circuit in chapter 4 was considering a voltage divider because the voltage was divided among all the resistors, a parallel circuit is considered a current divider circuit because we divide the currents. We manage the different routes the current, we control the different routes the current can take by playing with the current with the resistor values. So if I want more current in one branch, that branch better have a least or a smaller value for the resistors than the other different branches. So this is a little bit of designing right here. But the actual and the formal definition says that the KCL, the sum of the currents entering a node, is equal to the sum of the currents leaving the node. So here we are saying, we're introducing the word node. In KVL, we were saying across a closed loop. So in the examples and problems video for chapter 5, I will draw the node and I will explain how this works. But like in this example in the previous slide right here, this is a node. So the current comes here, the I source comes here, and here it hits the node. So this point, that point, and that point is the same point. So I can just squeeze them together and I can say that the current I source comes in, putting an arrow going into it, and then 3 arrows going out of it. So I know that they are going to be split in 3 different paths because I have 3 different ways. So this node contains 3 different paths in which my I source can be connected. Okay. So as we had a voltage divider for chapter 4, we have a current divider for chapter 5. So a current divider, when current enters a node, a junction, it divides into current with values that are inversely proportional to the resistant values. That inverse relationship is what tells us that the smaller the resistor, the higher the current through that branch. The most widely used formula for current divider is the 2 resistor equation. 4 resistors R1 and R2. So if I want to find the current going through the branch 1 or resistor 1, I'm going to divide or find the ratio of the opposite resistor by the sum of the resistors multiplied by the I total. In this case, I don't say I source because it might not be I source. We say I total because that is the total current entering that specific node. Like in this case, yes, it was I source because it was coming from I source, but it's not always the case. So the way they have generalized this form is by saying that the current in the current in I1 or in resistor 1 is equal to the opposite value resistor divided by the sum of the 2 resistors multiplied by the current entering that junction or that node. Likewise, if I want to find I2, it's always the opposite value resistor divided by the same sum. They both share the same denominator multiplied by the third current entering that junction. The resistors in the numerator is not the same as the one which the current is found. No, it's always the opposite, the one right across from it. That is in your book. If you would go in the book, there is a general form that extends this current divider to more than 2 resistors. Okay, so look at that. If not, I'll do an example where you'll see that we have the general case, not only for the two resistor equation that we are showing right here. So right here they are giving us an example. They are giving us the R1 is 2.2 kilo ohm resistors, and that R2 is a 4.7 kilo ohm resistor. So the total current is 8 milliamps. What is the current in each resistor? Before we do this mathematically and we have the answers right here, I want to point out that look at the ratio of the resistor values. R2 is double R1, so we expect that most of the current, at least twice the value of the current, is going to come through R1 because R2 has a higher resistor value. So if we were to divide this voltage into three, 2/3 would come to R1 and 1/3 would come to R2. And then let's do it mathematically, and we see that I1 is higher, almost double, almost double than the I2. So notice that the larger resistor, that the smaller is the current. So we have that again. We see that the inverse relationship we have between the current and the value of the resistor. Power in parallel circuits. Power in each resistor can be calculated with any of the standard power formulas, but since we always most likely will have the voltage, we will use this form where we have voltage squared divided by the value of the resistor, which is because it's more convenient. We don't have to find the current. As in the series case, the total power is the sum of the power dissipated in each circuit. So yes, power is independent. We calculate it the same way, and they will add up to the P total, whether it is a series circuit or a parallel circuit. So let's stop right here.